Calculus in Motion by Anil Kumar. Ace your calculus exam like a pro. We'll discuss a test quizzes on higher order derivatives in this particular playlist. Many questions are there. Feel free to contact us for the PDF. We'll discuss how do the objects move and how do we relate the velocity and acceleration. So, major takeaway for these questions are that we'll be given a displacement equation, which in this particular example is a polynomial. In following examples, we are going to change this equation to give you an overall view of how do we attempt all these problems. But the basic things remain, which are that the velocity is the first derivative of position. Acceleration is the second derivative of position, or you can say it is the derivative of velocity. And that is what brings us to higher order derivatives test, right? So there are many practical applications where we are looking into derivatives of derivatives. That is rate of change of rate of change. That is the objective. Now, with this simple example, we'll also understand when will the object be at rest. So it will be at rest when the velocity is zero. Makes sense, correct? Then we have an object speeds up. So speeding and slowing down are another two important aspects. So key to remember is that an object speeds up when the velocity and acceleration have the same sign. Perfect. And they slow down when they have opposite sign. That means if you multiply the velocity and the acceleration, you get something negative, means the object is slowing down, right? So that is how it is. We are going to end this video with a very beautiful graph which will explain and correlate all these things together. So once again, let's see what the question is for us. Position of a particle at t seconds moving along a straight line is given by s of t equals to 3t cube minus 40.5 t square plus 162t, where s is measured in meters and t is greater than equal to 0. Very common example, normally the very first example when you go to school will be shared by your teachers also. Now, what do you need to find from here? Find the particle velocity at a given time, which is 2 seconds for this example. Find particle's acceleration at 2 seconds. At what times is the object at rest? When is particle moving in positive direction? When is particle speeding? And the variation is when is particle slowing down in the negative direction, right? So we have added a term slowing down, not in both the directions, only in the negative direction. So read the questions very carefully in exam to get 100% marks, right? Well, I am Anil Kumar, and if you want to join my classes, join them, and then everything will be so easy for you to understand since we go in small steps a big way. Admission to the best universities, even with scholarships. Great. So let's begin with the solution. Great. So always begin with the equation given to us, which is displacement. In this case, is a cubic equation 3t cube minus 40.5 t square plus 162t. Find velocity, which is derivative of displacement, correct? Rate of change of displacement. So 3 times 3, 9t square minus 2 times 40.5 is 81t plus 162. Right. So from here, we can actually find the particle velocity as 2 seconds, right? So we can answer part A now, substituting time as 2, correct? So there we go, right? So it is 9 times 2 square minus 81 times 2 plus 162, right? You can use calculator, not an issue. Okay, so we have 4 into 9, 36. minus 162 plus 162, which gives you 36. Now, units are very important since they're asking you for velocity. You see, the units are meters per second, right? So, include the units meters per second. Makes sense. So, that was easy. Now, you see, the numbers are given in such a way that you really don't need a calculator. Correct? Concepts are important. Perfect. Now, let's get back to the part B where we need to find the acceleration at 2 seconds. So, what is acceleration? It is derivative of velocity, right? So, velocity was 90 square minus 81t plus 162. 9 times 2 is 18, so it is 18t minus 81. Find the acceleration when time is 2. So we'll just substitute 2 for t as we did for velocity. So we have 18 times 2 minus 81, right? So what you notice here is that you have a negative velocity, right? 18 times 2 is 36, and when you take away 81, what do you get? You get negative 45, right? Correct. And the units will be meters per second square. So rate of change of rate of change. You get the whole idea? Therefore, you get second square as a part of the unit in denominator. Perfect. So remember one thing, that means we have acceleration A as 45, negative 45, right? So important means it is deaccelerating, right? Minus 45 meters per second. So it means slowing down, deaccelerating. Correct? The velocity was positive 36 meters per second, means moving forward, right? Forward. Correct. So it is important to understand, since it's the beginning of our chapter and our understanding, we are slowly getting into very difficult questions from here onwards. So watch the playlist for many more questions to master these strategies. Correct. So let's move on to part C and D now. So what we have done here is we have written all the equations now. Displacement given to us as 3t cube minus 40.5 t square plus 162t, where t is greater than or equal to 0. Velocity we just found 9t square minus 81t plus 162. It has been factored now. You can take 9 common and then factor it very easily. And what you get here is bracket I forgot to write. So t minus 3 times t minus 6. Acceleration was 18t minus 81, has been factored, 9, 2t minus 9. That means acceleration will be 0 when at 4.5, 9 divided by 2. Right? Makes sense? Okay. Now let's continue with answering part C and D. At what times is the object at rest? So let's answer part C. Rest. Rest basically means that the velocity is 0, right? Now, velocity expression is what? So, I've written in factored form, which will be more useful. So, it's good to look into both the forms if possible. Correct. So, if I equate this to 0, we get 9 times t minus 3 and t minus 6. So, at t equals to 3 and at, 3, right? And at t equals to 6, we see it is at rest. So we can now write down at what times is the object at rest. So at 3 seconds, right? And at 6 seconds. Is that clear to you? The object is at rest. Is that clear? Always write down your answers with the units. Otherwise, you're going to lose zero point 0.5 marks and your chance of getting 100% marks. Makes sense. Great. Now let's answer part D, which is when is particle moving in the positive direction? Now, for positive direction, velocity has to be greater than 0, right? That is what positive direction is. Couple of ways you can make a table to check the values. But what I do at this stage, since we have a quadratic formula right there, right? So it's like a curve like this. Quadratic formula means a parabola, as you know, correct? And we are already having two zeros with us. One is at 3, the other one is at 6, correct? So, when we want to say moving in the positive direction, it means We have to start with 0, of course, because t is given to us, right? So we can say positive direction means velocity greater than 0 is from, we can say from 0 to 3, correct? And then from 6 onwards, right? So we can write 6. We can include 6 also, right? But not infinity. So that is how we can answer this part of the question. So very easy to use the graph, especially if you are working with quadratic or linear graphs, right? You don't have to make a table of values. But in any case, sometimes it is specifically asked to make a table of values. So no harm, we can do it, right? No problem, right? So just make table of values. We know t equals to 3 and 6 when it is 0, right? So we know the expression of velocity. I'm not writing here as the space is very less. Now, when you take a test point, so we can take test point 1, 4, and 7, for example, within this interval from 0 to 3, 3 to 6, and 6 to 7. So if I plug in 1 in my velocity expression, I will actually get a positive value. If I plug in 4, I'll get a negative value. And for 7, I get a positive value. And therefore, I get my solution that it is during the interval 0 to 3 and beyond 6 that the velocity is positive. Makes sense, correct? So that is how we are going to answer part C and D. Let's move on to the next part of this question. So part E is, when is particle speeding? Now speeding means what? Speeding means when the product of velocity and that of acceleration is positive. That is when it is speeding. Both are positive, correct? Now, in this particular case, it is kind of important to look at the graph itself. Hmm? So we just sketch the graph of velocity, which is given in the factored form right here. So what I will do here is now sketch some graph for you. Okay, great. So we start from some place where t is 0, which is 162 in this case. Okay. So this is not to the scale for sure. Okay. But anyway, that is how it is. So I made a small one here. So this is 3 and this is 6. And the graph is of velocity with time. Now, it is a part of exercise which we have not mentioned here. Explain and reason out or communicate with the help of something, and that something is graph for you. Okay. Now that's the velocity graph. Now let's sketch on this the acceleration graph also. So I'm sketching acceleration with green, which is a straight line as you can see, right? Minus 81, 18t, correct? And also from here, you can see that the acceleration given to us is actually 9 times 2t minus 9, correct? So when is this 0? So this will be 0 when 2t minus 9 is 0, or 9 equals to 2t. Let me write down, and 9 over 2 is t, right? Which is 4.5, right? What I'm trying to say is that this point here is 4.5 for you, right? So that is your acceleration. That point starting is minus 81. But here we have a point which is 4.5. So you see, from the graph, you can see when we have the same sign for velocity and acceleration. So one part, of course, is between this, correct? So let me shade this part for you. Both are negative, correct? Both are negative, correct? So this definitely is one part. And then after this, what we see is, sorry, I shared the wrong part, not this one. So how do I erase it now? Okay, leave it. So both are negative in this interval. Let me color it with a different thing. Right? So from 3 to 4.5, right? Both are negative, correct? So we'll say speeding is from 3 to 4.5, correct? As both are negative. And then after 6, correct? After 6, both are positive. So then it is union, right? After t, you get t greater than 6, right? So it is from 6 to infinity. Correct. So at this stage, we say they are speeding, right? Because at 3, Actually, the velocity becomes positive. Now, in some places, we do not include 3, right? So, what we do is we do not include these two in some places. Now, you need to ask your teacher about this part because I've seen solution including and not including also. To be on safe side, do not include while we are talking about speeding or slowing down, correct? So we'll keep the brackets there, not the square brackets. Perfect, makes sense. So that is how we are going to answer this particular question. And now for part F is, when is the particle slowing down in the negative direction? So when we say slowing down, it means that the product of velocity, so let's do part F now. Slowing down means velocity into acceleration is less than 0. So means opposite signs, right? For them, right? So seeing the graph, opposite sign is between 4.5 and 6, you can see. Because at 4.5, acceleration becomes positive from 0 and velocity is still negative. So that is when they are actually speeding. Now, slowing down. Now it says, when is particle slowing down in the negative direction, right? So negative direction means when it is when velocity is negative, correct? And slowing down means opposite. So the answer is from 4.5 to 6, correct? Because velocity is at this time, there are a couple of things. Velocity has to be less than 0. So velocity is less than 0 between 3 to 6. Within this interval, acceleration becomes positive after 4.5. And therefore, that is the region where while the velocity is negative, means reverse direction, the car or the object is slowing down. Makes sense, right? Great. So that is how we'll answer this. Now, to summarize all this, what we have done is we've taken a very beautiful graph, a bigger one. We had been just squeezing things in earlier, but that makes everything absolutely clear. Is that clear to you, right? So I like you to, go through this graph, understand. So the yellow line is actually the velocity, right? So this is the velocity. As you can see here, velocity is given by this yellow curve, and it is positive. Velocity is positive in these portions shown in green, right? And it is negative right there. And what we have not included here is the acceleration graph, right? So at 4.5 we saw that this acceleration was moving kind of like this, correct? So from here, you can see the last answer was acceleration becoming reverse of sign, becoming reverse of negative of velocity. So it was this portion which is slowing and reverse negative velocity. Do you understand? And that gives you the summary of all our answers. It, I'll appreciate if you sketch this graph and then neatly write down the different intervals. What is happening in each, right? So this is the portion where velocity is positive, acceleration is negative. That means it is still slowing down, right? This is also slow, but this is slowing down when velocity is greater than 0. So that is not part of F to be answered. So make a note of this, right? So with that, we come to an end of this beautiful example. Based on what you have learned in this playlist, we are going to have many questions. We'll approach higher order derivatives in the reverse way also. That is, I'll give you the graph and then ask you different questions of when is it speeding, when is it slowing down, just as we had here. Plus, we'll give you extra practice with different kinds of equations, maybe rational and radical equations, which makes it complicated. I hope it makes sense. Feel free to write a comment, share your views. If you like and subscribe to my videos, that'd be great. Thanks for your valuable time and all the best.